Yeah, so good evening, everyone. I hope you are having a good day. So, in case you do not know, my name is Bhavya. I am a PhD scholar at IIT Madras. I'll be doing these problems solving sessions every Tuesday on at 6 p.m. So, let us begin the session. So, this session will be a short one. So, I may not cover entire 2 hours, probably 1.5 hours at the max. Not many questions because um, uh, I mean, firstly, there is only a particular kind of question that you can pose at a certain level, and also because, especially in induction, there are certain kinds of questions you can ask until you talk about other mathematical structures. So, yeah, I've prepared a few questions and we'll solve them one by one. So, this time's topic is mathematical induction. And it also has a second part to it, which is pigeonhole principle, which is different from mathematical induction. Of course, they may be used together. So, as always, I'll just briefly revisit on what the topic is about. Like, for example, induction. So, induction is actually a very powerful proof technique in mathematics. Okay, so there are theorems in mathematics to which we only know the proofs, inductive proofs so far, and non-inductive proofs so far we do not know. I mean, such is the power of induction. Okay, and you can prove a lot of things in different ways, but mathematical induction is one way to go about it, and it's really powerful. For example, in the lectures you may have seen that the question on number of subsets of a set could be proved using combinatorics, as bit strings and so on. It could be proved using set theory itself, and it can be proved using induction also, as you saw in the lectures. So, what is induction? So, induction is simply this idea that it is often compared with the rungs of a ladder. So, if you can reach a particular rung of a ladder, then you can reach the next rung of a ladder, and therefore you can climb the entire ladder. Or sometimes it's explained in terms of dominoes. That if one domino falls, okay, if the first domino falls, and somewhere in the middle another domino falls, then the domino in front of it will also fall. So the entire sequence of dominoes will fall. I mean, this is the kind of statements you'll try to prove with mathematical induction. For example, um, so the statement that we usually prove in induction is, based on a certain parameter. For example, here I have written, some statement P is true for every n. I say um, something like 1 plus 2 plus so on. Okay, I claim something like 1 plus 2 plus so on. This is my statement. Okay, P is equal to plus n, okay, is equal to some n times n plus 1 divided by 2. Right, this common formula. But how do you prove this? I can say, like, okay, when n equals 1, okay, when I can say when n equals 1, then this then the sum of first 1 plus nothing, right? So n is itself 1, so 1 equals 1. Okay, but also side by side, what we do, we can set 1 to be equal to n, and 1 plus 1 divided by 2. We can check if the formula is correct, and we got 2 by 2, which is equal to 1. Correct. Next, n equals 2, then 1 plus 2 equals 3. Then you can do 2, then 2 plus 1, because n equals 2, right, equals 6 divided by 2, which is equal to 3. And then you can continue this way. But this doesn't guarantee anything, right? This does not guarantee anything that how long do I do this process of checking? I cannot check for every natural number n that there is there, because natural numbers are infinite. And it may so happen that my formula given here may satisfy for 1, 2, 3, and so on until 100, and suddenly after 101 onwards, this formula does not work for us. Getting it? So therefore, how do you prove for really big quantities? When you talk about infinities and so on. Good. Someone is here. Okay. So how do you do that? How do you prove for really big quantities? And therefore you use techniques like induction. So what is the idea? The idea is as follows. So what we need to prove is that the statement P is true for every n. For example, here this statement that 1 plus 2 plus and so on till n is equal to n times n plus 1 by 2 for every n. This is what we need to prove, and we do what is called the base case. Base case is that for some foundational case, okay, for example, when 1 plus 2 plus and so on, take the simplest case possible. So the simplest case in this case is like something like n equals 1. For example, when n equals 1, I proved that this formula holds. N equals 1 is that first domino in that domino example I give, or the first rung of the ladder. I need to show that my person is capable of climbing the first ladder. Only then can I show that the remaining rungs in the ladder can be climbed. Okay, so base case. This is what the base case is all about. Now, once you prove base case, okay, you prove that P is true, the statement is true for the base case. Then what you do? You do an assumption of what is called the inductive hypothesis. This is also commonly called IH. Okay, IH. The inductive hypothesis, you do not need to prove the inductive hypothesis. Always keep in mind, you are only supposed to assume it. You assume that P is true for some n equals k. Okay, P is true for some n equals k. Then what you do is you do the inductive step, which means you prove P is true when for some n equals k plus 1. One step more. Okay, you do this, and when you and how do you do this? You use the inductive hypothesis. You use the previous rung of the ladder to show that this rung can also be climbed. So one moment. Yeah. So for example, this statement itself, 1 plus 2 plus and so 3 plus 4 plus until n, okay, equals n times n plus 1 divided by 2. How do you prove using induction? What is the first step? The first step is the base case. Okay, so the base case is as follows. When n equals 1, we've already done it actually, sum of first one natural numbers, first one many natural numbers, which is 1 itself, is equal to 1, and then you have that n times n plus 1 divided by 2 is nothing but 1 times 2 divided by 2, which is equal to 1. So base case holds. Similarly you do for the others. Similarly what you do is Similarly, what you do is you assume the inductive hypothesis, assume IH, okay. And what is the IH? The IH is as follows, for 1, okay, or you can directly say 1 plus 2 plus 3 plus so on till n is equal to, till some k, okay, let's say k, is equal to k times k plus 1 divided by 2. Okay, some intermediate value. Okay, for some k greater than 1. Okay, you assume the inductive hypothesis. Now what you do? Now what you do is you need to show 1 plus 2 plus 3 until k plus 1. This is the inductive step. Equals. So this is your n now. Therefore, what will happen? K plus 1 times k plus 1 plus 1 divided by 2. Getting it? So now all that this means is that now how do you do this? So what is this equal to? 1 plus 2 plus 3 until k plus 1. But 1 plus 2 plus 3 plus still k is nothing but k times k plus 1. Why is this? This is because of inductive hypothesis. Because in the inductive hypothesis, we assumed this to be true. That sum of first k terms is equal to k times k plus 1 divided by 2. Okay, so now all you do is now you simplify it. Okay, now all you do is you simplify it. You do k times k plus 1 plus k plus 1 plus 2k plus 1, I think, right? Plus 2k plus 1, right? Whole divided by 2. Next, what do you have? This is nothing but k plus 1 common, right? And you do k plus 2 divided by 2, which is nothing but k plus 1, k plus 1 plus 1 divided by 2. And these two are equal. So we've proved it. We've proved the entire statement. So this is how induction goes. Okay, so this is a simple example of induction. First thing is we prove the base case. Okay, when for a very simple value of the parameter, very simple value of n, we prove the statement. Okay. Next, what you do, you assume the inductive hypothesis, which means you simply assume the statement for some k when n equals k. Now, next, what you do, you move to the next ladder, next rung of the ladder. So if you assumed for k, you now prove for k plus 1. Prove for k plus 1, not assume for k plus 1, mind you. Okay, you need to prove that the sum of first k plus 1 numbers is equal to this n times n plus 1 divided by 2. But here n is k plus 1, so k plus 1 times k plus 1 plus 1 divided by 2. And where you should necessarily use the inductive hypothesis. Okay, you should necessarily use the inductive hypothesis to prove this. And yeah, now because of the principle of mathematical induction, you prove the entire statement. So that is the idea. Well, so please stop me if you have any doubts in between. So let's for now I'll move on, but let me know if I need to stop somewhere. Okay, so the question is as follows: the sum of first n odd numbers is n times n minus 1, okay, n square, n plus 1, 2n plus 1. This is the question. So you can use guessing, or you can use some trial by error or something to get this. So if anyone wants to tell what the answer for this is. The sum of first n odd numbers. Okay, Lakshmi says B. What is B? B is n square. Okay. Okay. Yeah, yeah, good luck. The answer is n square. The answer is B. That's correct. Yeah, let me reduce the space. I don't need so much space here. Yeah. So the answer is B. That is true. Now, firstly, what we can do is we can do some trial by error thing. So, firstly, let's say first one odd numbers. Okay, or I'll simply do when n equals 1. When n equals 1, the sum is equal to 1. When n equals 2, okay, when first odd numbers they are saying, okay, so 1, 3, 5, 7, and so on, is equal to 1 plus 3, which is equal to 4, and n equals next odd number is 5, then sum equals 1 plus 3 plus 5, which is equal to 9, and so on. So you can already see that n square satisfies this. Well, if I have to give a quick answer, then n square would definitely help, right? But again, like as I said before, how do you prove this for the entire sequence of odd numbers? How do you do this? How do you prove this for the entire sequence of odd numbers? Is something we want to know, and you can use this. You can do this using induction. So it's quite simple. So what you do is now you Lakshmi n equals key. That's right. Yeah. So that's the inductive step, right, Lakshmi? Yeah. So so what is the claim we want to prove is that 1 plus 3 plus 5 plus and so on. Okay. And the first n terms, nth odd number, is equal to n square. So here to prove this, what I'll use is I'll use some fact, okay, which you can verify. The ith, okay, odd number, okay, is given by 2 times I minus 1. Okay. For example, when first odd number, this is the formula for odd numbers, generating odd numbers. 2 times 1 equals minus 1 equals 1. Second odd number equals 2 times 2 minus 1, which is equal to 4 minus 1, 3, and so on. So ith odd number is 1 plus 3 equals 4. Gomati is written n equals 2, 1 plus 3 equals 4. Yeah, that's right. When n equals 2, 1 plus 3 equals 4. Yeah, that's right. So if I have to find, now I know that, so if I want to find the odd number at position I, then I use this formula, 2 times I minus 1. Okay, good so far. So what now I do is, let me look at the base case. Okay, since 1 is the first odd number, okay, sum of first one odd number is equal to 1 itself. There's nothing after 1, right? This is the first odd number, right? So 1 itself, and let us use a formula now. So when n equals 1, n square equals 1. So these two are matching. The sum given and n square is matching. So the claim holds here. So base case is proven. We are all fine. Okay. So the claim is n square will be the correct formula, and it is correct formula when n equals 1. Next, what we want to do is you want to assume the inductive hypothesis. Okay. So the assumption is sum of first k odd numbers. So here nothing but you are assuming n equals k, okay, is equal to n square, but n equals k, so you assume it is k square. Okay. So now need to prove the inductive step. So I need to prove that claim is that sum of first k plus 1 odd numbers equals k plus 1 whole square. Now this is when n equals k plus 1. Now by the principle of mathematical induction, if I prove this, I'm done, right? So now what I do is I look at this 1 plus, in other ways, another way to state it is 1 plus 3 plus 5 plus and so on until kth odd number plus k plus 1th odd number equals k plus 1 whole square. This is what we need to prove, is it not? So now what we do is we use the inductive hypothesis. Inductive hypothesis says the sum of first k odd numbers is k square. So 1 plus 3 plus 5 until the kth odd number is nothing but the sum of first k odd numbers, right? So this is nothing but k square plus k plus 1th odd number. Okay. Why is this true? Because of the inductive hypothesis. By inductive hypothesis. Okay, good. Next, what do we want to do? Now, how do you do the final simplification? We know that the ith odd number is given by this formula. This formula. Ith odd number is given by 2 times I minus 1. So, which is equal to nothing but k plus 2 times k plus 1 minus 1, right, by fact used above. Let me call that 1. Okay, by fact number 1. Next, what I do is I simply simplify it. K square plus 2k plus 2 minus 1, which is nothing but k square plus 2k plus 1, which is nothing but a square plus 2ab plus b square. So this is in that form, a square plus 2ab plus b square. So this is nothing but a plus b whole square. So it is true that sum of first k plus 1 odd numbers is k plus 1 whole square. So we've not only proved for 1, 3, 5 or 1, 3, 5, 7, we've proved for the entire set of odd numbers. So this is the power of induction. Okay. Okay, good. So yeah, this one I'll not be doing because this one is in the similar flavor. Okay. It will be but the document will be uploaded to you, so you can take a screenshot right now, or you can look from the document, and please try this offline. This has a very similar flavor to it. Okay, all you need to use is the formula for a plus b whole cube. Okay. Okay, so now that is done, okay, or if you would like to take a screenshot, I'll just leave it here. Also, if there was a question in the previous question, if there is a doubt in the previous question, let me know. Okay, let's move on now. So the question is as follows: prove that 3 to the power n is less than 6 factorial if n is an integer greater than 6. Okay, now even doing it um, by hand is actually it is a bit difficult, right? Because you need to calculate factorials and powers and so on. But you can try it, of course. Like integers greater than 7, they are saying. So you can try it for 3 to the 7 is greater than 6 factorial. Oh, wait, there's a problem here. What is the problem? shouldn't be 6 factorial. How can it be? This is a constant. Okay. This is n factorial. I think this is n factorial. Yeah. Sorry. This is always less than 7 factorial. You need to prove this statement. Okay. I mean, you can do it by hand. And so let's try it. 3 power 7, right? Let me open up the calculator. Or if someone can do it side by side, then also good. Now let's do 3 power 7. 3 power 7. 3 power 7 is 2187. 2187 less than 7 factorial. Is there a factorial? Yeah, 7 factorial. 5040. So this is true. But like, we cannot pop out a calculator and do this each time. No, 3 to the power 8 is less than 8 factorial and so on. But you can get a feel of it using this. And how do you prove for the entire thing? You'll use induction. So yeah, so my claim is 3 power n is less than n factorial for all, n greater than equal to greater than 6. So let's prove by induction. Okay. And by induction on n. Now, in any inductive proof, you need to write the base case. So I ask you, what should be the value of n for the base case? What do you think should be the value of n for the base case? Should I begin from 1, 2, some? Gomati says 7. Yeah, that's right. Yeah, good. We should begin from 7 because remember our theorem asks, the claim asks for n greater than 6, strictly greater than 6. And since n is an integer, okay, the only n which is strictly greater than 6 is 7, right? So we begin from 7, right? Because the claim starts only from n is greater than 6. So the base case is n equals 7. So, but well, the good news is, we've already calculated that, so 3 to the 7 is nothing but 2187, and 7 factorial is nothing but 5040. So we have that 3 to the 7 is less than 7 factorial. Okay, so the base case is done. Base case holds. Now let's look at the next thing. IH, inductive hypothesis. I inductively assume this. Okay, inductive hypothesis is that n 3 to the k is less than k factorial for some k greater than 7. Okay, I assume this and assume IH. So this is what I assume. Next, what I need to do is I need to prove for k plus 1. To prove 3 to the k plus 1 is less than k plus 1 factorial for not for the same key. This is what I need to do. So how do I go about doing this? So let us look here. Now 3 to the k plus 1 can be written as 3 times 3 to the k. right? That because powers add up on multiplication is less than k plus 1 times k times so on till 1. Let's say 2 times 1. Okay. Now what is 3 times 3 to the k? It is less than k plus 1 times, this is a factorial in itself, it is k factorial times k factorial, right? Now observe here properly. Since k is greater than 7, this implies k plus 1 is also greater than 7, right? This k plus 1 is greater than 7, which implies that k plus 1 is greater than 3 always. Getting it? So this quantity is always greater than 3. Okay, this quantity is always greater than 3. And suppose somehow this quantity was supposed to be less than the left hand side, it can only be that k factorial is less than 3k. But that is not the case, right? Because by inductive hypothesis we know that k, so we know that 3 to the k is less than k factorial, right? 3 to the k is less than k factorial, or in other words you can also do which means that 3 times 3 to the k is less than 3 times k factorial, which means that 3 times 3 to the k is less than k plus 1 times k factorial, because k plus 1 is greater than 3. Okay, the main thing to observe here is that by inductive hypothesis we already know that this quantity is less than this quantity. Now in order to prove this inequality we just need to show that 3 is less than k plus 1, and we already know that k is greater than 7, so k plus 1 is greater than 7, which means actually k plus 1 is greater than 8 also, but I'm not mentioning that. K plus 1 is greater than 7, which means that k plus 1 is greater than 3 also. So we have that k plus 1 is greater than 3 and k factorial is greater than 3k. So this entire right hand side is greater than the left hand side. And therefore we've proved, which is nothing but 3 to the k plus 1 is less than k plus 1 factorial. Done. Okay. So yeah, I hope it was clear to everyone. The another important thing here is about the base case. Okay, since we are taking, we are trying to prove this claim for n is greater than 6, we need to start from something that is greater than 6. Otherwise, if that was not the case, then we would have proved a stronger claim, right? We would have proved for n is greater than 5 or 4 or something else. Okay, I hope that was clear to everyone. If not, please let me know. Okay, let's move on. So yeah, here the question says prove that. So let me increase the size. Go. So the question says the following: prove that 1 by 2 plus 1 by 4 plus 1 by 8. You observe that these are all powers of 2, 2, 4, 8, 16, 32 and so on, plus so on until 1 by 2 to the n for some n is equal to 1 minus 1 by 2 to the n. So now this claim can also be done by induction, very similar to the previous ones. Okay, so by induction on n, if there are multiple parameters, you can decide what to do induction on. If there was m also, then you could have done induction on m. Suitably choose your induction parameter. Now by induction on m, now we need to do base case when n equals. So can someone tell me what the base case should be? So what should the base case be here? Okay, I mean, if there is difficulty finding the base case, the go-to approach is always look at the simplest term that is there. I mean, break it into the simplest form possible. So what is the simplest form of this problem? When there is only one term in this expression, and it only occurs when the only term is, yeah, good going, one. That is the answer, right? So as I was saying, the only case when it occurs is when there is only one. I mean, the only case when only one term is there, when you are taking the sum of the first one term. Okay, so base case is when n equals 1, because 1 by 2 to the n is nothing but 1 by 2, which is the first term itself. So now you are beginning your induction here. Now you will proceed to the other terms. Okay, so when n equals 1, you have 1 by 2 on the LHS. Okay, now besides it, what you have, okay, the question you are asking is 1 by 2 is equal to 1 minus 1 by 2 to the n or not? Well, 1 minus 1 by 2 to the n is 1 minus 1 by 2 to the 1, right, which is nothing but half, and 1 minus half is half, so you have that they are equal. So yes, so this formula is good when n equals 1. Next, what you do, inductive hypothesis is assume statement when n equals k, right? You need to assume the statement when n equals k, that is 1 by 2 plus 1 by 2 to the 2 plus 1 by 2 cube plus so on till 1 by 2 to the k is nothing but 1 minus 1 by 2 to the k. This is what you assume. Okay, next what you do, inductive step, show that 1 by 2 plus 1 by 2 square plus so on until now 2 to the k plus 1 equals 1 minus 1 by 2 to the k. So let's say plus 1 by 2k plus 1 by 2k plus 1. Okay, but again, by inductive hypothesis, we already know that the first k terms is nothing but 1 minus 1 by 2 to the power k, right? So this is nothing but 1 minus 1 by 2 to the k, right? And plus 1 by 2 to the k plus 1. Okay, this is by IH, inductive hypothesis. Now what do I do? I can take that LCM or something, but a simpler way to do it would be like, which is equal to 1 minus 1 by 2 to the k plus 1 by 2 times 2 to the k. Okay, which is equal to 1 minus, now take 1 by 2 to the k common, and so this becomes 1 minus 2 to the k. Okay, if you take it common, then the minus will, so it's better to do this as plus and minus 1 here and plus 1 by 2 here. So when you take it common, this is what you get. The minus comes from this minus here. Okay, and which is nothing but 1 plus 1 by 2 to the k. Minus 1 plus half is minus half, which is equal to 1 minus 1 by 2 to the k times 2. Okay, which is nothing but 1 minus 1 by 2 to the k plus 1. And whatever we wanted to prove is proved. So, I mean, how I recommend how it to solve inductive based things is, you look at the inductive step and you somehow want to see a pattern where you can fit in the inductive hypothesis. For example, when you broke it into some terms, okay, when you broke it into these terms, some of these terms, then you get that these terms, the first k terms is exactly those which feature in the inductive hypothesis. So most of inductive hypothesis actually relies on such kind of methods. Okay. So let me know if there is anything related to induction that you want to ask. But besides that, we'll only be solving these many questions in induction. We have a few more questions in pigeonhole principle. Okay. Now we'll look at pigeonhole principle. And this is another very powerful technique in mathematics, and it is used all over the place. Okay, and it's used to prove very very non-trivial places also, surprisingly. And it might seem obvious, but it is very strong. The statement says the following: if there are n plus 1 pigeons in n holes, then there is at least one hole with 2 pigeons. Well, looking at the first glance, I mean, it is quite obvious that if you have these holes, and you have only n holes, and you are trying to fit n plus 1 pigeons, and well, if I put one pigeon everywhere, okay, then I'm left with 1 pigeon. So if I'm saying that n plus 1 pigeons I've put in these holes, it means that at least 1 pigeon is staying in one of the holes. So the question is, I mean, the statement is saying that there is at least one hole with 2 pigeons. So this is simply the pigeonhole principle. So you might say, like, what if I distribute it differently? Say I put, I don't put all the pigeons in all the holes. I distribute, in fewer holes, and I leave one hole empty. But if I leave one hole empty, I'll need to put, more pigeons in these holes. So these holes actually become the holes where you put the extra pigeon. So the pigeonhole principle is not valid. Well, but there's another slightly more explorative variant, okay, which is called the generalized pigeonhole principle. So the principle says the following: if there are n pigeons in k pigeonholes, okay, and here k is less than n, okay, if there are n pigeons in k pigeonholes, then there is at least hole with ceiling of n by k many pigeons. Here what does ceiling mean? The nearest greatest integer. Okay, for example, ceiling of 3 is nothing but 3, but ceiling of 3.1 equals 4. The nearest greater integer. Okay, so 3.00001 is 4. Okay, but you can see for the case that 3, the nearest greater integer, okay, greater than equal to integer, is actually 3. So yeah, this is what is meant by ceiling, because k may not always absolutely divide n, right? So so if there are k many holes and you are putting n pigeons, there is at least one hole with n by k many pigeons. Okay, and I think you've seen the proofs in the lectures. It is not very difficult. It's by contradiction, and we'll be using generalized pigeonholes also, left and right. So yeah, let's look at the questions. The questions are the following. Um, okay. So, okay, I'll do this question later. Yeah, first we'll do this. Okay. So the questions are the following. What is the minimum number of students required in a discrete mathematics class to be sure that at least 6 will receive the same grade? If there are 5 possible grades, A, B, C, D, F. Okay. Now the suggestion. Is there a message here? Okay. Yeah. So so suggestion I give here is always that for example, to be sure that 6 will receive the same grade, wherever objects share the same place. Okay, if they share the same place, example, 6 students are sharing the same grade, then make that shared place your pigeonholes. Okay, and whatever are whoever people are sharing, make them the pigeons. Okay, so for example, in this question, 6 students are sharing the same grade. It means students are the pigeons, and grade are the pigeonholes. Okay, so now how many pigeonholes are there? How many? So this means number of. Okay, so number of pigeonholes equals 6, equals 5. Why? Because they are A, B, C, D, F. These are the holes. So the idea is as follows. I make 5 holes. Then I look at each student, and I will put the student in the hole with whatever grade they receive. Okay, so let's say there are 5 students. Okay, let's say there are 5 students. I put one student here. I put another student here, another student here, another here, another here. So is my answer guaranteed that at least 6 will receive the same grade? No. I mean, here none of the holes have at least 6 people. So if I have, let's say, 6 students, well, I could say that, oh, okay, put all the 6 students here and remaining put 0 people. But in this particular case, this is getting satisfied, right? But we are saying we need to be sure that any distribution we are doing, 6 people should be there. All right. So, because another way I could distribute the 6 people is like 1, 2, 3, 4, 5, and 6 here. So, how many people are here? Total 6 people, but there are all of them. Okay, none of the boxes, none of the pigeonholes have at least 6 students. So even 6 students don't do. So what we need to do is we need to increase the number of students so much that at all of them will have at least 6 people. So there is a logical way to think about it also, and there is the formula way of thinking about it. Well, the logical way of thinking about it is, um, well, okay, I'll tell the formula way first. So, uh, formula way is as following. We use the formula of generalized pigeonhole principle. Okay, so generalized pigeonhole principle says that n by k, okay, at least n by k students in each hole, okay, which means that n by k students get same grade, right? So n by k students get the same grade. So what is n by k for us? At least 6 people should get the same grade. So n by k is 6 for us. At least n by k students get the same grade, which is nothing but at least 6 people. And what is k here? But k equals the number of holes, which is 5. So n by 5 equals 6. Now, I can simply multiply 5 and get 30, but they are asking for the minimum. So since this is floor, okay, I don't look for, the closest, I look for the closest nearest integer that will go to. For example, here I'll explain what I mean. For example, what I'll do is, I'll do, what is n by 5 such that n by 5 is strictly greater than 5. Okay, so if I do n equals 25, then n by 5 equals 25 by 5, which is equal to 5. But we need something strictly greater than it. But n is an integer. Remember, we cannot do something like 25.5, 25.6, and so on. We need to look for n equals 26. We add one more, and n by 5 equals 26 by 5, which is equal to 5 point something. Or we can even see it in the calculator. 26 by 5 is 5.2. Which means ceiling of n by 5 is the nearest greater integer, which is ceiling of 5.2, which is equal to 6. Now this bound is tight, when n equals 26. We could have directly multiplied 5 to 30 and got the value of n, but that was not tight. That is not the minimum we can do. The minimum we can do is when n equals 26, because when n equals 5, we already have that, it is already 5. So, but ceiling of 5 is still equal to 5, but we want the ceiling to be equal to 6, right? So I hope everyone understood this notion, okay, of how to calculate this. Okay, I cannot simply multiply 5 times 6 because this will not give me the minimum answer. Okay. Okay, good. So next we'll move on to this one. Oh, okay, and what is the logical way to think about it? If I distribute, okay, so that I avoid at least one of the boxes as six many. I can put one here, one here, one here, one here. So I'm still avoiding. I can put two here, two here, two here, two here. I'm avoiding so far. Well, I can avoid until this distribution occurs 5, 5, 5, 5, 5. After this, any pigeon I put, I cannot avoid anymore. After this, if I put a pigeon here, let's say, then this will become 6. Then, there is this one pigeon hole where at least 6 people sit, 6 pigeons sit. So, if I put it here, then, this will become 6 and, this will get violated. So, the logical way of seeing it is that, 5, how many people are there now? So, when I put one more, okay, to this, it becomes 26. So if I have 26 pigeons in these pigeonholes, I'm guaranteed to have one. I mean, at least one box with 6 people. At least 6 people. Okay. There should be one more question, but I do not see the question. Okay, it seems like I pasted that image twice. Okay. Well, okay. So this is another question in the same flavor. Okay. What is the minimum number of students, each of whom comes from one of the 28 states, must be enrolled in a university to guarantee that there are at least 5 students who come from the same state? So this is the question. So yeah, can you tell me? Firstly, can you tell me what is the pigeon and what are the pigeons and what is the pigeonholes? What are the pigeonholes? Akansha says state is the pigeonholes. Yeah, good. And pigeons? Students is the pigeon. Good. Right. So again, I tell you that and why are objects that share something should be the pigeons, and the thing that gets shared, take it as a pigeonhole. Okay. So here, they share the same state. The question is saying. So if they share the same state, then the state is the pigeonholes because it is the object that is getting shared, and the objects that share are the students. The students are sharing the states. Okay, good. So now, like the previous question, can you tell me what is the answer to this? Oh, okay, there's a typo here. Okay, if I point out the typo, then you will get the answer. But I'll point out the typo once I tell you to attempt the question once. So don't look at the options. So without looking at the options, can you tell me, because the answer does not feature in the options? Ah, right. Yeah. Okay. Akanksha says 113. Yeah, that's right. The answer is 113. So I guess you understand where the typo is now. So this should be 3. Okay, I remember that I changed the typo here, and it seems I removed another question here. Yeah, so this is the actual question here. Okay. Okay. Or did I not remove? Okay, it's behind. This is what had happened. Okay. Anyway, um, yeah, right. So the answer is 113. Why? Well, you know, so number of pigeons, which is nothing but k, pigeonholes, which is nothing but k, is equal to number of states. How many states are there in India? 28. Right. It's given in the question also. And this is pigeonholes, and they are saying at least five. They are saying. And what does the statement say? Generalized pigeonhole principle says that at least n by k, ceiling of n by k, right? So generalized pigeonhole principle says at least ceiling of n by k share same hole. Here at least five share same pigeon, sorry, state, which means that 5 is your n by k. Okay, so and what is k here? N by um, and n is the pigeons, so n equals number of students. So what is the k here? K is your 28, the number of states you have. So n divided by 28, okay, the ceiling of that should give you 5. So like I told you, don't do this, don't do 28 times 5 directly. You'll get 140. But you want this is still a valid answer, that okay, at least this many will be there, but minimum that many will need not be there, right? So this may not be the minimum optimum answer that you want. So what you do is you choose the nearest um, uh, value that will give you need some value of n such that n by 28 equals 4 point something something. If such a value doesn't exist, then well and good, you just do 28 times 5, but you need 4 point something here, right? So the most obvious thing to do is you divide by n minus 1. Oh, what I mean is you do 28 times 4. Okay, so uh, so okay, 140, right? So you get that 20, or you rather do that 28 times 5 is 140. So do 130. Okay, yeah, do n by 28 equals 4. That is n 4 times 28. So look for the closest one. 4 times 28, 112, right? So until 112 everything is fine, but as soon as you increase 1, but 112 plus 1 equals 113. Now this will not be divided by 28 exactly. Okay, 113 divided by 28 will give you 4 point something something, which means that 113 divided by 28, ceiling of this value will give you 5. Okay, Therefore your answer is n equals 113. Okay. So yeah, this question, could you take a look here? Maybe you can even answer it. But once the idea is that once you know what the pigeon and pigeonholes are, then you can do it. Okay. The question is saying there are 38 different time periods during which classes at a university can be scheduled. If there are 677 different classes, what is the minimum number of different rooms that will be needed? So, there are 38 different time periods in the school, and if there are 677 different classes, and you want to do it in a way that you want to organize the classes in such a way that you know um, at the same time period, okay, at the same time period, you don't run out of classrooms. Okay, in other words, right? So you know the idea is that we want to avoid sharing classrooms. Okay, we want to avoid sharing classrooms. So since you are sharing classrooms, okay, since you are sharing classrooms, okay, and among classes, okay, since you are sharing classrooms will be your pigeonholes, and classes will be your pigeons. Okay, so the idea is as follows. If you find out that after so what are the number of classrooms? So number of pigeonholes is so number of, oh yeah, so it, oh okay, sorry, you're sharing classes, I'm sorry, very sorry, you're sharing time periods, that's right, sorry, right. We want to avoid sharing time periods, right? I mean, or rather, if they share the same time period, we want to allocate different classrooms to them. Yeah. So therefore, the time periods become your pigeonholes, which is nothing but 38, and the classes become 677. So what does the generalized principle say? There exists, okay, there exists at least one time period where n by k, okay, here this is nothing but k, this is nothing but n, ceiling of n by k, um, classrooms, where no, not ceiling by n by k, classrooms, um, n by k classes are held in the same time period. Okay, there is at least one time period where um, all the classes are held. At least this many classes are held. Okay, so how many classes are held during that time? 677 divided by 38. Ceiling of this. Okay, so what is that? 677 by 38. 17.8. Ceiling of 17.8, which is equal to 18. So 18 classes. Okay, there is a box. There is a uh, I mean, no matter how you distribute, okay, no matter how you distribute, there is at least one classroom. There is at least one time period where 18 classes are held. So what is the solution for that? Solution: allocate 18 classrooms. And now for that distribution where there are 18 uh, there are 18 classes, okay, in that one classroom, and the remaining, okay, in that particular distribution, the remaining are guaranteed to be less than 18, right? Because we already saw the logical way to do it would be scatter 17 17 each and then add one to it, and therefore that is the distribution to it, everything 17 17 and so on, and that is given by this formula. And so 18 classroom if you give, there will be no class room, okay, or rather there will be no class which will be without a classroom. Okay, there will be no class without a classroom, without a classroom. Okay, so this is the answer. Well, okay, so we move on to the last question and then we'll wrap up the session. Okay, the question says okay, but if there are any doubts, please let me know. Well, we can think of it logically also. You know that this n by k, okay, this n by k just represents the fact that you are putting n by k many um, elements in each of these boxes. In other words, in uh, each of these time periods, you are putting these classes n by k many classes. N by k happens to be 17. So now what you do is you add one more to it, then 18 will be there. Now there is a classroom with at least 18 many time periods, and which means that for this you can always do with 18 many classrooms because others are all 17 or less. Okay, so yeah, let's look at this final question. Question is as follows: Consider an 8 cross 8 chessboard. In the following statement true or is this following statement true or false? It is impossible to place 9 non-attacking rooks on the chessboard. Now, what is a rook? If you play chess, then you will know that if I have a chessboard, this is quite a simple question. If you have a chessboard and then I have a rook, okay, look something like this. A rook is only allowed to move straight on either the row it sits at or column it sits at. It's talking about non-attacking rooks, right? What does it mean by non-attacking rooks? If two rooks, okay, if or any rook is non-attacking, if there is a chess piece, okay, that it can attack, it can eat. If it can attack this, then this rook becomes an attacking rook. So the question is simply asking the following. Is it possible to place 9 rooks on the chessboard such that all of them are not able to attack each other? Okay. So, again, there are two ways to answer it. One logical way and one using the pigeonhole principle. Either way, please think about this question, whether the answer of this statement is true or false. Oh, okay. Akanksha says false. Okay, I'll give a few moments for the others to say whether it's true or false. Akanksha says, sorry, it's true, we can't place 9 rooks in. Oh, okay. Yeah, the statement is in a negative form. It's saying it's impossible. Okay, yeah. Right. So it is saying is it true that you cannot do this? Okay. 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 Yeah, Akanksha, you are right. The statement is true. It is not possible to do this. Well, logically, what is the idea that if I place it in any way, they will somehow attack each other. So let's say I place one here, I place one here, I place one here, and so on, trying to avoid each other, because if I had placed it here, then these two are attacking. So I cannot place the two of them there. Yeah, and I place one here, I place one here, I place one here, and I place one here. And how many? Okay, so this is 8 by 8. So I have a total of 9 rooks in my hand. I have placed 8 rooks. I have 1 remaining in my hand. Okay. Where do I put that remaining rook? If I put here or here or here, or any column for that matter, it will, the rook at that particular position will always attack me. Okay. So if I place it here, then this rook will attack me. If I place it here, then this rook will attack me. So logically it is not possible to do, because I looked at the best case possible which avoids all the attacking positions, and yet when I add one more to it, one more rook to it, it does not work for me. So yeah, logically it is, the statement is true. What is the pigeonhole principle way to do it? Oh yeah, this is a good question. So what do you consider the pigeonholes at here? Can you tell me? What could be the pigeons and what could be the pigeonholes? Rows and column, rooks are pigeons. Um, Rows and columns. So you mean there will be 64 pigeonholes, Akanksha? Because there are 64 squares. So do you
No,
mean?
sir.
Oh, okay.
Sir, the rook can attack vertically down and horizontally first row, the top rook. So
Right.
that whole column and whole row, I can take it as one pigeonhole. So
Right.
there will
Right.
be total 8 pigeonholes.
Okay. 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 Yeah. Good. So yeah. Um. So Akanksha is saying that um, this I can consider as the first pigeonhole, and this I can consider as the second pigeonhole, and let's see, this I can consider as the third pigeonhole, and so on, right? Or maybe you mean this also and this also, right? And yeah, that is correct. You can do this. Okay, the pigeonholes, okay, is the row plus column of each rook, and so how many are there? Which means 8 pigeonholes. Now there are 8 pigeonholes, and what are my pigeons? Pigeons are my chess pieces, which is rooks, which is 9. So 9 is greater than 8, which means there exists at least, okay, or there exists, yeah, there exists at least 2 rooks in the same hole. That is, 2 rooks, one rook in some other rook's row or column. Okay, let's call this rook 1, and let's call this r2, which means that r2 can attack r1, because if they belong to the same row or they belong to the same column, then r2 can attack r1. Yeah, that's right, Akansha. I mean, that's true. And but we can even make it simpler actually. The simpler way to do it would be, uh, if, okay, let me just copy this. Oh, forgot to copy. Oh, insert. An even simpler way to look at it is, the following way. I will remove this. Oh, I will remove this here and this, and I'll remove this, and so on. Now what I do is I just look at pigeonholes as rows of chessboard. Okay, I just look at rows of a chessboard. And how many rows are there? 8 rows. How many rooks are there? 9 rooks. Which means there exists 2 rooks in same row. Right? There are 2 rooks in the same row. And if there are 2 rooks in the same row, the 2 rooks are attacking, since they belong to the same. Okay, I mean, this is another way to look at it. So you can get rid of the columns also. Actually, you can just look at rows. Okay, with that we come to the end of the session. This was the final question. So if you have any more questions, please let me know. I have recorded this session, so it will be there on YouTube by tomorrow. By tomorrow noon, it will be ready. Okay, and even this document itself. So yeah, if you have any more questions, then please stay and ask me the questions. Otherwise, you are free to leave. Okay, have a great day. Okay, yeah, thank you, Akanksha. Okay, happy Teachers Day. Oh, okay. Thank you, Akanksha. Okay then. Gomati, do you have any questions?